In the furthest reaches of our nearby planet group, past the circle of Neptune, something uncommon is occurring. A puzzling force is pushing around frigid objects, and groups of these items have surprising circles that can't be made sense of by the known planets alone. Researchers think this could be brought about by a monstrous, stowed-away planet, frequently called Planet 9. First proposed in 2016, this potential new planet has interested cosmologists. Strangely, this isn't the first time a planet has been proposed using science. Neptune and Pluto were both found because their gravitational impacts were anticipated before they were seen through a telescope. Stargazers saw anomalies in the circles of Uranus and later in the Kuiper Belt objects, prompting the revelation of these far-off universes. A century after the fact, we find ourselves in a comparable situation with Planet 9, following this interesting custom of utilizing numerical predictions to uncover stowed-away planets. Some researchers accept it could have been a rogue planet caught by our sun's gravity, while others think it may have formed from the same circle of gas and dust as the other planets. If Planet 9 exists, it is believed to be multiple times more massive than Earth and to orbit the Sun at a distance of 400 to 800 astronomical units, which is 400 to 800 times the distance between the Earth and the Sun. Stargazers have been anxiously hunting for hints, utilizing powerful telescopes and advanced computer models to track its impact. After years of watching the sky, solving numerical conditions, and running complex simulations, they now have the strongest evidence yet that Planet 9 truly exists. This discovery presents an exciting twist in the tale of the hidden planet. So what proof did the specialists reveal in their chase after Planet 9? If we have found exoplanets many trillions of miles away, why has it been so challenging to distinguish Planet 9 directly in our astronomical backyard, even with some of the most powerful telescopes available to us? Although Planet 9 was first proposed in 2016, its story began not long after the revelation of Uranus in 1781. Over the years, space experts noticed something strange. Uranus wasn't moving precisely as their estimations anticipated. It appeared to accelerate and decelerate in its orbit, indicating that there might be a concealed force acting on it. During the 1840s, two mathematicians, Urbain Le Verrier in France and John Couch Adams in Britain, independently proposed that the uncommon movements of Uranus could be caused by the gravitational pull of a concealed planet. They used complex mathematics to predict where this invisible planet might be found. This was a bold hypothesis, relying entirely on numerical calculations to suggest the presence of an unknown world. Le Verrier sent his predictions to Johann Galle, an astronomer at the Berlin Observatory. On the evening of September 23, 1846, Galle and his assistant pointed their telescope to the part of the sky Le Verrier had indicated. Incredibly, they found Neptune on their first night of searching. This accomplishment was remarkable, as it was the first time a planet had been discovered through numerical prediction rather than by chance observation. After the successful discovery of Neptune in 1846, cosmologists thought they had a complete image of the significant planets in our nearby planet group. However, when they tracked Neptune's orbit, they found that Neptune, like Uranus before it, showed slight deviations from its anticipated path. These anomalies were subtle but consistent. Given the success of using gravitational forces to predict Neptune's presence based on the orbit of Uranus, stargazers wondered if a similar method could uncover yet another planet even farther out. This led to the discovery of Pluto. More than 80 years later, on February 18, 1930, Clyde Tombaugh, a young cosmologist at the Lowell Observatory, identified a faint, distant object moving against the background of stars, confirming the presence of another celestial body. Initially hailed as the long-sought Planet X, Pluto was later found to be much smaller than anticipated. Pluto's mass was insufficient to account for the gravitational anomalies observed in the orbits of Uranus and Neptune. This implied that something else was out there beyond the circle of Neptune that hadn't been discovered yet. In 1951, Dutch-American astronomer Gerard Kuiper predicted that there could be not one but several cold objects beyond the circle of Neptune, and Pluto was just a part of that larger belt of objects known as the Kuiper Belt. The first direct observational evidence of Kuiper Belt objects, KBOs, came in 1992 when astronomers David Jewitt and Jane Liu discovered 1992 QB1, a small icy body beyond Neptune. This discovery confirmed the presence of a population of objects in the area Kuiper had predicted. As more objects were discovered beyond Neptune, The term transneptunian objects, TNOs, was introduced to encompass all objects circling the Sun beyond Neptune. TNOs are a broader category that includes any small body in the solar system that orbits the Sun at a greater average distance than Neptune, 30 astronomical units or more. The discovery of Sedna in 2003 added to this interest. Sedna, another large TNO with a highly elliptical orbit, has a perihelion, closest approach to the Sun, of around 76 astronomical units and an aphelion, farthest point from the Sun, of around 936 astronomical units. In the following few years, more extreme TNOs were found. There is something strange about the orbits of TNOs. Imagine you scatter many marbles on a flat surface. Typically, you would expect the marbles to be spread out randomly. But if many of the marbles are strangely clustered in one specific area, it would suggest that some force or mechanism is pulling them together. This situation mirrors what researchers have seen with TNOs. Their orbits are not randomly distributed but show clustering. Normally, if TNOs were orbiting randomly, their paths around the Sun would be spread out in all directions, much like the marbles in our analogy. Their perihelion points would be at different places in the sky, not clustered in one area. However, their perihelion points tend to be grouped in one part of the sky. This clustering is highly unusual and suggests that there is a common factor influencing their orbits. Moreover, the long axis of their orbits, the lines connecting their closest and farthest points from the Sun, are aligned in a way that is statistically unlikely to happen by chance. This alignment further supports the idea that an external force, possibly the gravitational pull of a large, concealed planet, is at work. The consistent direction of these orbits provides strong evidence for the hypothesis that Planet 9 is exerting its influence from afar, shaping the orbits of these distant objects. Building on the discoveries of Sedna, other TNOs, and additional research, the hypothesis of a distant, unseen Planet 9 gained significant momentum. In January 2016, cosmologists Konstantin Batygin and Mike Brown published a groundbreaking paper that further solidified this hypothesis. They analyzed the orbits of 6 distant TNOs and suggested that these patterns could be explained by the gravitational influence of a previously unknown planet. They proposed that this theoretical Planet 9 would be around 10 times the mass of Earth and orbit the Sun in a highly elliptical path, ranging from 400 to 800 astronomical units. When Neptune was found, it happened surprisingly quickly. Space experts found it on the first night of searching based on numerical predictions. However, the search for Planet 9 has proven to be far more challenging. There are 4 main issues. The first is its distance. Planet 9 is believed to be 10 to 20 times farther from Earth than Pluto. At such a significant distance, the planet would receive very little sunlight, making it almost undetectable against the background of stars and difficult to distinguish with current telescopes. The second issue is that Planet 9's orbit is likely highly elliptical. This means it could spend most of its time in the most distant and darkest regions of its orbit, far from the Sun's illumination. When it is at these farthest points, the planet would be even faint. And harder to detect. The third issue is the vast area of the sky where Planet 9 could be found. This wide search area requires cosmologists to meticulously scan large regions, often rechecking and verifying observations to ensure nothing is missed. Finally, the planet's slow movement across the sky complicates detection efforts. Due to its large distance from the Sun, Planet 9 moves slowly relative to the background stars. This slow movement means identifying it from the background stars requires prolonged and repeated observations. Stargazers must carefully track potential candidates to confirm they are moving objects, not just fixed stars. Given these challenges, simulations become a key tool in the search for Planet 9. Simulations enable researchers to model complex systems and predict behaviors that are difficult or impossible to observe directly. Let's examine how scientists use simulations to find the strongest statistical evidence of Planet 9. The orbits of TNOs are not stable over long periods. Over millions of years, Neptune's strong gravitational pull can alter their paths, scattering them widely or even ejecting them completely from the nearby planet group. This dynamic demonstrates that TNOs are constantly driven into orbits intersecting with Neptune. To explore this further, a research team set up simulations based on the initial conditions assumed for the formation of the inner Oort cloud. The Oort cloud is thought to be a distant spherical shell of icy bodies circling the solar system, extending from around 2,000 to 100,000 astronomical units from the Sun. They chose TNOs with perihelia greater than 30 astronomical units and semi-major axes ranging from 100 to 5,000 astronomical units, resulting in a simulation of 10,000 particles. The research team ran two sets of simulations, one including the speculated planet 9 and the other excluding it. In the first scenario, the team incorporated the hypothetical planet 9 into their simulations. By observing how this additional gravitational force influenced the behavior of other objects, researchers could identify patterns and anomalies indicative of Planet 9's presence. In the second scenario, the researchers removed Planet 9 from the simulations to compare the outcomes. By contrasting the results from both simulations, researchers could assess whether the presence of Planet 9 explained observed celestial phenomena more effectively than without it. The simulations ran for 4 billion years, the approximate age of the solar system. This extended timescale allowed researchers to study the cumulative effects of Planet 9's gravity on the orbits of distant TNOs, providing valuable insights into the long-term dynamics of the outer nearby planet group. The simulations involving Planet 9's existence provided compelling evidence for its presence, with significant deviations in TNO orbits. In these simulations, TNOs were observed to cluster at perihelia greater than 250 astronomical units, revealing a distinct pattern influenced by Planet 9's gravity. This clustering was more pronounced and aligned than seen in the second set of simulations without Planet 9. Without the presence of Planet 9, the simulations produced far more randomized and dispersed TNO orbits. In this scenario, the clustering observed in the first set of simulations was absent, indicating that Planet 9's gravitational influence played a crucial role in shaping these celestial patterns. This compelling evidence from the simulations strongly suggests that a substantial planetary body, Planet 9, exerts a significant gravitational influence on the orbits of distant TNOs, providing the most robust statistical support to date for its existence. Please continue. ChatGPT. However, despite the compelling evidence from simulations, direct observation of Planet 9 remains elusive. Researchers must continue refining their search strategies and using cutting-edge technologies to overcome the challenges of detecting such a distant and faint object. The discovery of Planet 9 would not only confirm its existence, but also enhance our understanding of the formation and evolution of the outer solar system. Until then, the hunt for Planet 9 continues, driven by both scientific curiosity and the tantalizing possibility of unveiling a hidden giant within our cosmic neighborhood. In the broader context of planetary science, the search for Planet 9 highlights the dynamic and ever-changing nature of our solar system. The idea that a significant planet could remain undetected in our cosmic backyard for so long challenges our assumptions and underscores the need for continuous exploration and observation. As telescopes become more powerful and our observational techniques improve, the potential for new discoveries grows, reminding us that the universe is full of surprises waiting to be uncovered. While the search for Planet 9 is ongoing, it also sparks interest in the possibility of other hidden celestial bodies beyond the known planets. The outer solar system, with its vast and largely uncharted regions, may harbor more secrets than we currently imagine. Each discovery adds a piece to the puzzle of our solar system's history, revealing the complex interactions and events that have shaped it over billions of years. The quest for Planet 9 also underscores the importance of international collaboration and the pooling of resources in the scientific community. Large-scale projects, such as the search for distant planets, often require the combined efforts of astronomers, engineers, and researchers from around the world. By working together and sharing data, scientists can make significant strides in uncovering the mysteries of the universe. In summary, the story of Planet 9 is a testament to the enduring spirit of scientific inquiry and the power of human curiosity. It reminds us that even in the 21st century, there are still vast unknowns waiting to be explored within our own solar system. As researchers continue their search, the potential discovery of Planet 9 promises to deepen our understanding of the cosmos and our place within it. Continue. ChatGPT. As researchers continue their search for Planet 9, advancements in technology and methodology play a crucial role in enhancing our ability to detect and study distant celestial objects. Here are some key aspects of how future efforts might progress. 1. Advancements in telescopic technology. Future telescopes are expected to offer even greater sensitivity and resolution, allowing astronomers to detect fainter and more distant objects. Upcoming projects like the Vera C. Rubin Observatory, with its large-field survey capabilities, will be instrumental in scanning vast areas of the sky and identifying potential candidates for Planet 9. The next-generation space telescopes and ground-based observatories, equipped with advanced imaging and spectroscopy instruments, will also contribute to this effort by providing more detailed observations of distant regions. 2. Enhanced computer models and simulations. Improvements in computational power and algorithms will enable researchers to run more sophisticated simulations and analyze complex dynamical models of the outer solar system. These simulations can help refine predictions about Planet 9's potential location and orbit, guiding observational strategies. Additionally, advancements in machine learning and artificial intelligence may enhance our ability to process vast amounts of data and identify subtle patterns indicative of Planet 9. 3. International collaboration and data sharing. Collaboration among international research institutions and observatories is crucial for the search for Planet 9. By sharing data and resources, scientists can pool their expertise and increase the efficiency of their search efforts. Joint projects and global initiatives will help coordinate observations, share findings, and develop new techniques for detecting distant planets. 4. The role of citizen science. Citizen science projects can also contribute to the search for Planet 9. Public engagement in astronomy and data analysis can help process large datasets and identify potential candidates. Platforms that allow amateur astronomers to participate in the search for celestial objects can augment professional efforts and contribute valuable insights. 5. The potential for new discoveries. The search for Planet 9 is not only about finding this specific planet, but also about expanding our understanding of the outer solar system. The discovery of Planet 9 could lead to the identification of other hidden objects and provide new insights into the formation and evolution of our solar system. Each discovery, whether it's Planet 9 or other distant objects, contributes to a broader understanding of the cosmos. 6. The impact on cosmology and planetary science. The confirmation of Planet 9 would have significant implications for cosmology and planetary science. It would validate theories about the distribution of mass in the outer solar system and potentially reshape our understanding of planetary formation and migration. The discovery could also influence theories about the origins of our solar system and its interactions with neighboring star systems.